Hey all, in this video we're going to go back to learning more about induction. So far we've really only learned about induction on natural numbers, which is sort of the classical induction that mathematicians have used and studied for a long time. In computer science, structural induction, doing induction on data structures, is I think much more common. I almost never do in my work inductions on numbers. I almost exclusively do inductions on the interesting structures that I'm defining. So let's see how it works. Let's do it by example. We can just kind of compare notes and sort of see how what we're doing relates to and is different from doing induction on a natural number. The general gist is going to be pretty similar. We're going to assume something about a substructure, and use that to prove something about a superstructure, and then prove something about a starting point, and then that's going to let us build some tower or knock over some dominoes or your other preferred metaphor. So tactic-wise, super concretely in Coq, we'll use the induction tactic and the patterns just change to accommodate our data type. So where we had a zero case and a successor case, we now have a nil case and a cons case. Okay, the cons case takes extra stuff, right? Successor, we would just say n prime and our IH. Now we say, okay, well, here's the head of the list, here's the tail of the list, and because it's a substructure, I'm going to give it an IH, and we get a pattern that looks something like this. Looking at our cases, you can see that substituting in for L, we have the two possibilities for a list. We have an empty list, we have a con sum L prime. These are the two ways that L could be formed. They correspond to the two cases we'll have to prove. This one's our base case, this one's our inductive case, and we can expect to see an inductive hypothesis when we get there. Let's do the base case first. In the base case, we have empty list append m append n ought to be equal to empty list append m append n. Okay, if you don't see why this is not a big deal, maybe we can look at the definition of app again. You can look at it and say, oh, wait a minute. It's just going to match on the first thing. If it's empty, it's just going to return the second thing. So here, this will be inert. We'll just return m plus n. Here, this will be inert. We'll just return m. So that's going to be m append n. I said plus a second ago. Fair enough. There's a bunch of plus signs. We simplify. They are syntactically equal. What could be better? Let's look at the inductive case. So what have we assumed? Well, for our substructure L prime, we've assumed the property we want to prove. And what is our goal? Well, for extending that substructure with one level of constructor, right? So the cons of some A onto the front of it. Now what happens here when we run simple? Utterly delightful. So what simple is doing here is over here, it's pulling that A off over here. So that A becomes on the front of the whole thing. And here, the A will pull off of this whole subquantity, and we'll get A cons L prime append M. And then of this whole thing, this will be A cons L prime append M, append N, and then the A will come off of that. So when we do simple all the way, Coq says, hey, these two things both have an A cons on the front, and then, ooh, look what we have behind. Look what else, this matches this exactly. This matches this exactly. Fantastic. Rewrite by our IH, L prime, excuse me. Right, here it seemed to choose left to right. It doesn't matter, right, because the two parts are equal, and we're done. Okay, let's see that proof informally. Right, for all A lists L1, L2, L3, L1 append L2 append L3 is the same as L1 append L2 append L3. Okay, let it all be given by induction on L1. In the base case, we have to show this, that empty append L2 append L3 is the same as empty append L2 append L3, but that's immediate. Okay, next, suppose L1 is equal to n cons L1 prime. We can assume as our inductive hypothesis that L1 prime append L2 append L3, right, that is equal to L1 prime append L2 append L3. Now what do we have to show? Well, our L is equal to this, our L1. So we have to show that A cons L1 prime append L2 append L3 is equal to A cons L1 prime append L2 append L3. But the way plus is defined, we can reduce both sides to look like this. But then the rest of that, this is just the inductive hypothesis that this part is equal to that part. And so we're done. Okay, there are a bunch of exercises here for you to play with. In the next video, I'll show you this lemma about binary trees. Talk to y'all soon.